When you look at a globe, you can see the many mountain ranges on our planet. They're found on every continent. Globes can be very useful. But to understand more about mountains and how they're created, we have to look deep inside the Earth. The Earth's interior consists of several different layers. The inner core, which is believed to be solid iron and which is very hot. The outer core, which is believed to consist of rocky material so hot and under such great pressure, it is in a liquid state. The mantle, which is not so hot as the outer core and not so liquid. The mantle's outermost portion is solid. This is the solid outer portion of the mantle. Above this is the outermost layer of the Earth, the crust. Together, the crust and solid outer portion of the mantle form the Earth's outer shell. They are referred to as the lithosphere. It's not always easy to see the Earth's crust. It is covered by vegetation and oceans. But if you could drain the oceans and strip away our planet's vegetation, the Earth might look something like this. Now you can see the Earth's hard outer shell. And if you look closely, you can also see the shell is cracked. The red glowing lines mark the places where the Earth's shell is cracked into small and large pieces called tectonic plates. Each plate carries a continent or an ocean basin, or sometimes both. The plates are moving 1 to 2 inches a year, carrying continents and ocean basins with them. Millions of years ago, the world looked something like this. Every continent in a different position. They were so close together, they formed a single supercontinent called Pangaea. But even then, the plates were moving, a few inches a year, and kept moving until they reached their present-day positions. The theory that continents move is called continental drift. When you look at a globe today, you are looking at only a moment in time, because the continents are still moving. In millions of years, scientists expect the world to look entirely different. Every continent in a new position. Here's why the plates are moving. Scientists believe material in the mantle is circulating, much as it is doing here. The circulating movement may be caused by heat within the mantle. You can get an idea of how heat can cause a circulating movement by watching rice as it boils. What you see happening within this beaker is similar to what's happening within the Earth's mantle. As mantle material moves, perhaps only inches a year, it causes the plates above it to move as well. In some places, plates are moving in opposite directions. They are moving apart. The area where two plates are moving apart is called a divergent boundary. In other places, plates slide past each other. The area where two plates slide past each other is called a transform boundary. And in other places, plates are colliding. Most of the world's great mountain ranges occur where two plates collide, an area called a convergent boundary. Here's what happens at some convergent boundaries. In this example, the plate on the left is carrying a continent and is moving in this direction. The plate on the right is also carrying a continent, but is moving in the opposite direction. They are colliding. The two plates squeeze up against each other. Under the incredible pressure, layers of the Earth's surface are compressed and folded, rising high into the air. These raised layers of Earth are called folded mountains because of the way they're folded. You can make your own folded mountains simply by squeezing the ends of some towels together. The Earth's crust will fold just as these towels will. The world's highest mountains, the Himalayas, were made in much the same way. They were formed when the plate carrying India collided with the Eurasian plate. Over millions of years, the Earth's crust was squeezed into folds more than 5 miles high. Today, the Himalayas are growing even higher as the plate carrying India continues to push against the Eurasian plate. It's not always easy to see the folds because the mountains have been worn into jagged peaks by water, wind, and ice. But if you look closely at mountains like these in North America, you can see how rock has been folded under the great stresses caused by moving plates. This outline gives you an idea of what these mountains may have looked like when they were much younger. When Mount St. Helens erupted in 1980, it reminded people that some large mountains are actually volcanoes. In a matter of seconds, much of Mount St. Helens was blown away, the mountain literally losing its top. Dense clouds of volcanic ash and debris poured out of a newly formed crater for days on end. Carried by the wind, the ash was blown hundreds of miles, burying towns and cities, turning day into night. The pictures you are now looking at were recorded in mid-afternoon. The eruption left a ghostly wasteland. Trees toppled like matchsticks. Vehicles tossed about like toys. Crews were brought in to search for the dead and injured. All told, 62 people were killed. Forests and animal life were wiped out. And at the mountain's summit, a new crater, nearly 2,000 feet across and 500 feet deep. Mount St. Helens is but one of many volcanic mountains situated in the Pacific Northwest states of Washington, Oregon, and California. None of the Pacific Coast volcanoes are currently erupting, but you can tell they are volcanoes. Unlike most other mountains, they stand alone, great distances between them. And unlike the jagged peaks of other mountains, the shapes of most volcanoes are symmetrical. One side matches the other. As with folded mountains, the Pacific Coast volcanoes occur near a convergent boundary. The plate carrying the ocean basin is moving in this direction, and the plate carrying the continent is moving in this direction. Here's what happens. Because the plate carrying the ocean basin is heavier, it will dive beneath the plate carrying the continent. As it does so, tremendous heat and pressure are created, causing solid rock to liquefy into a material called magma. Magma is similar to lava that erupts from volcanoes. The magma rises in large globs into the plate carrying the continent. Eventually, the magma stops rising. Some of the globs may form a magma chamber. As more and more magma adds to the chamber, pressures build. Some of the magma finds its way to the surface, where it can erupt. Mount St. Helens erupted in much this same way. Some volcanoes occur far from plate boundaries. The Hawaiian Islands are thousands of miles from the nearest plate boundary. Yet this area is among the most volcanically active areas in the world. Scientists believe a hotspot exists in the Earth's mantle below Hawaii. Hotspots are areas where magma has found its way through the Earth's crust, emerging on the ocean floor, where it becomes hardened by cold ocean water. More magma follows, adding to the formation of an underwater volcanic dome. The dome becomes larger and larger, and may, after thousands of years, rise above sea level. Every island in the Hawaiian chain, as well as many others around the world, was formed in just this way. Seldom do hotspot volcanoes erupt with the explosive force of volcanoes like Mount St. Helens. But what they lack in explosive impact, they make up for in showy displays. Lava fountains are typical of these kinds of volcanoes. The lava can shoot hundreds of feet into the sky, and an eruption like this can last for days. Lava can also erupt through cracks in the ground, creating walls of fire, or lava curtains. A lava curtain can sometimes be more than a mile long and reach a height of over 150 feet. When lava travels downhill, it can create rivers of fire. In some places, the lava slows to a stop, hardening into black rock as it cools. But in other places, the lava doesn't stop, reaching the ocean. Steam explosions are common as the lava explodes as it hardens. New shorelines form under clouds of hissing steam. When watching scenes like this, it's easy to forget that the Hawaiian Islands are actually mountains, volcanic mountains. These mountains in Wyoming are examples of a third type of mountain. They are called fault block mountains. Here's how fault block mountains are created. The Earth's crust is filled with cracks, the way this rock is filled with cracks. Some cracks in the Earth's crust are called faults, and faults are places that are important to scientists. One side of a fault tries to move in one direction. The other side may try to move in the opposite direction. But the two sides are locked in place. They can't move until enough stress builds up to move them. If you bend a stick slowly, you will find it won't break until sufficient stress builds up. That's what happens deep underground. The fault will remain locked until enough stress builds up, and then it will suddenly release, as one side of the fault slides past the other with a tremendous burst of energy. The energy that is released is in the form of seismic waves, which radiate or move outward. If you've ever thrown a stone into a pond, you've seen waves move outward in all directions. The waves in this pond are similar to the waves caused by movement along a fault. If the disturbance is big enough, the waves will eventually reach the surface, where they can cause considerable surface movement, which is referred to as an earthquake. Each year, there are thousands of earthquakes throughout the world. While most are small, some are large, like this one, which struck California. 67 people were killed, and damage was widespread. So what does all this have to do with fault block mountains? Well, some faults reach all the way to the Earth's surface, and over millions of years and countless earthquakes, one side of the fault may rise above the other side. The uplifted section may rise miles into the sky. Mountains made this way often have one side that is very steep. These fault block mountains rise nearly 2 miles over the valley beneath them. This line shows how one section of the Earth's crust has risen above another section.